This is a short video presentation on accurate prediction of bounding boxes in object detection. In this video, I will talk about the ideas presented in the paper Bounding Box Regression with Uncertainty for Accurate Object Detection by He et al. Currently, there are several challenges in object detection and localization. Some of the challenges are shown here. There are various ambiguities in the ground truth bounding boxes in object detection datasets. There might be some incorrect labels as well in large-scale object detection datasets like MSCOPO. Objects in images might not be clearly visible due to occlusion. For example, the back of the car is not visible due to the person in front. Moreover, more object detection models use smooth L1 loss, which is not always suitable for bounding box regression. Also, these models give higher localization confidence score to boxes with high classification score, which might not always be true. For example, in the bird image, the box with lower classification score is much more accurate. In this project, the intention is to use KL loss introduced in the paper by He et al. And reproduce some of the results. In the paper, predicted box coordinates are modeled as Gaussian distributions and ground truth box coordinates as direct delta functions. The predicted localization variance from Gaussians are used in computing box regression loss. Also, to choose better bounding boxes, a method called variance voting is used, which is similar to soft NMS. In KL loss, the KL divergence between the predicted Gaussian and ground truth delta distribution is calculated. The loss is similar to smooth L1 loss, where the variance is considered as 1. The loss depends on alpha, which is the log of the variance. Hence, the detection network is set to predict alpha. In the variance voting algorithm, weights are assigned to candidate detections such that the boxes with larger intersection over union gets higher score, and boxes with lower variance gets higher score. The voting mechanism does not depend on classification score, as we know that higher classification score does not necessarily mean higher localization confidence. This method can be used along with soft NOS as well. In this project, I have implemented these two main algorithms using PyTorch. The authors have already provided the official implementation in Cafe 2 using Facebook's Detektron framework. For this project, I have used an object detection backbone model called Faster RCNN ResNet 50 FPN pre-trained on MS-COCO data. I modified the architecture to predict the localization variances and incorporated KL loss and variance putting algorithms on top of that. I trained the model on Pascal POC 2007 data and tested it using the validation set. I also compared the results with the existing implementation using the mean average precision metric. Firstly, some experiments were done with an already existing implementation based on detection tool on a small subset of MS-COCO data. Further ablation experiments were performed on the Pascal POC dataset using the custom implementation. As shown, the results were found to be close to that in the original paper, but it was lower than expected. The model did not perform well in detection of small objects, as can be seen from low APS value. These are some of the sample detections. It is observed that the model with KL loss outputs almost the same number of candidate detections as that without KL loss. Several improvements can be done on top of the current code. The algorithms can be tested using other background models as well, like VGG16. The model can be trained for longer time using more GPU resources for better results. Larger datasets like MS-COCO can also be used for improving the results. The algorithms can be incorporated into Facebook's Detektron 2 framework via configurations. These methods provide insight into the probabilistic approaches for better modeling of population uncertainties, which is an area of future research. Thank you.